Come on. There we go. All right. So I hope you all had a good weekend. So last Thursday we were talking about, we essentially continued on with our conversation of truth tables, and we talked about how things can be logically equivalent. We discovered the contrapositive and converse, and then we started looking at we finished one of these big problems that truth tables can be used for. They're a little tedious, but it's essentially where you assume everything they tell you is true. You fill out the truth table and then select the correct rows where everything you assume is true, and then you come to your conclusion. So we have one more of those to go over, and then we move on to 1.2. So here we go. So say what we have now is we have that if Andy is hungry and the refrigerator, actually I want to talk about one thing before I start. Sorry. As long as I pushed it through correctly, and I think I did, I'll triple check it right after class. Your first homework should be up on WebAssign. So it would have popped up today and it'll be due next Tuesday at 11:49 p.m. So we run on a Tuesday to Tuesday kind of schedule with homeworks. So Tuesdays, just write this down really quick and then I'll erase it. 11:59 p.m. Is when your homeworks will be due. I can grant extensions, but there's a slight penalty on extensions depending on the situation. If it's like a dire situation and you just really couldn't get to it, then it'll be fine. But if it's just like, I unfortunately missed it, there'll be a small penalty. It's not the biggest thing in the world on that. Anyway, so Tuesdays to Tuesdays. I feel like there was one more thing I wanted to say about that, but I can't remember what it is. Oh, yes, there is. So, in the homework, there's like a various type of problems you'll see. Some of them are like completely fill in the blank. Some of them have a drop-down box and you choose, and some of them are multiple choice. Essentially, okay, cool. Are you saying it? Hold on. Let me bring that up real quick. So essentially, depending on the type of question, you're going to essentially have n-1 chances to try it. So what that means is if it's a, sorry, I'm trying to do two things at once. If it's a multiple choice question with 5 options, you have 4 chances to get it right. If it's a drop-down box with only 2 choices, you only have 1 chance to get it right. So actually what I want to do real quick, so yeah, it is, okay, let me unshare this screen and share this other screen real quick. There we go. So you should see the homework on your page. Here it says due Tuesday of next week. So that's good. So yeah, so on something like this where it has 5 choices, you'll have 4 chances to get it right. The one thing I want to say is on truth tables. So since it's only a true false option, you only get 1 chance. But what I would suggest is doing it column by column, because what you can actually do is you can just submit half the answer. And see what you got wrong and what you got right. So that way you don't fill out the whole entire table and get half of it wrong when you could just keep going column by column. And obviously if you get that wrong, then it's the other one. So you can kind of submit along the way if it's got multiple parts to it. But that's kind of how those work, is if it's got 5 choices, you got 4 options, 4 chances. If you got 2 chances, you have, 2 options, you have 1 chance. And then things like this, it's just forever. Also with the fill in the blank ones, as far as I understand from what I've seen on, this is only the second time I've ever used WebWork, but from last semester, I believe it pretty much accepts anything you put in there. So I suggest actually trying to put something that would be right. And if you want to triple check with me to see if your answer was right, you can do that. I also don't do a lot of these. Like this one kind of slipped in there because it was part of another question that I liked. So there's not a lot of completely fill in the blank because it doesn't really check for right or wrong. It just gives you points for it. But don't completely stress out on those open-ended ones. And then, so we'll be going over this stuff today. So again, here you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 choices, so you'd have 10 chances to get that right. That kind of deal. So there are a couple of these down here. Again, anything you put in here is right. I'll put up some, I'll try to remember. Remind me if you want to see it. I'll try to put up the full answers for these once the homework's due in case you want to check yourself. But I'll talk about that a bit more when we get into today's notes. Anyway, so that's how the homework goes. That's up now, and it'll be due next week. So. Oh, no. You can come back to it as many times as you want. So you can start it now, come back to it in 2 days, do some more, come back to it in a few more days, do some more. And it's possible that I'm going to try to, keep it as close to what we're doing as possible. Well, obviously the homework's going to be over what we're doing, but it could be a case where if it pops up on that Tuesday, we might still be covering stuff on Tuesday and potentially part of Thursday. So it's possible that you might not be able to do it all right at the start. But no, you can do, excuse me, you can come back to it as many times as you need. All right. Dun, dun, dun. I think that was everything I wanted to talk about. Yeah. All right. So let's start notes now. So our statement, if Andy is hungry and the refrigerator is empty, then Andy is mad. Suppose Andy is not mad and the refrigerator is empty. Is Andy hungry? So let me do a little bit of setup first. So let me try to block this off so I have enough space. So I'll do my truth table over on the right. So let's say I'm going to let H be Andy is hungry. I'm going to let R be the refrigerator is empty. Again, you can choose whatever letters float your boat. I just like to use ones that kind of go with the wording. And then I'll use M for Andy is mad. So the first thing we should do is essentially write down what we know, because that's essentially what we need to put in the truth table. And what we know is essentially what they tell us. So they tell us if Andy is hungry and the refrigerator is empty, then Andy is mad. So notice there's an if and a then, and there's kind of an and between them. So the and statement is going to be part of the if. So we're going to have essentially an and statement in here implies something else. So if Andy is hungry, so we have an H, and the refrigerator is empty, so H and R. So if H and R, then Andy is mad, so it implies M. Then we're told, suppose Andy is not mad and the refrigerator is empty. Now, I'm going to say something and then let me clarify a little bit. So there is an and in here, but now you can go one of two ways. You could use that and or not. I usually choose not to because it adds an extra step and it's not worth it. The reason I can choose to ignore this and I couldn't ignore the first and is because the first and was contained in an if then. So if something's contained in an if then you have to use it. But since this is on its own, there's no if then here, I can essentially split those into two separate statements. So suppose Andy is not mad would give me not M. And then the refrigerator is empty would give me, would give me R. So again, technically, if you wanted to, you could have made this not M and R, but what that's going to do is it's just going to make you have to do one more column on the truth table. So I just choose to separate them. So again, if it's in an if then, you can't separate it, but if it's outside of an if then you can just write them down separately. So again, with these things that we know, we're going to assume they are true. So now what we need to do is we need to create that really big what is the words that's coming out of my mouth? We need to create the kind of big, long truth table and then select the correct rows that have all of those things being true. So we have an H, and R, and an M, and it's going to be in 8 rows, so I need a lot of space. And that's a very bad line. And then we're going to need to essentially have all of those things show up. So I need a not M, I already have an R, so that's fine. And I need an H and R implies M. So remember with the larger ones, we always split them up. So I'm going to find an H and R first. And then I'll be able to do the H and R implies M. And then I'll put my conclusion over here. So remember, we need all the combinations of true falses here. So I like to make half of the first one all true and then the other half false. And then if I have 3 variables, the second column I like to make in batches of 2. So it's essentially 2 true, 2 false, 2 true, 2 false. So true, true, false, false, true, true, false, false. And then the third column when we have 3 is just essentially every other. So true, false, true, false, true, false, true, false. And remember, you don't have to do it in that exact format. The large majority of people I have ever met do it in that format. But as long as you have all of the combinations, it's fine. It's much grosser to grade, if I'm quite honest, but whatever floats your boat if you like to do the falses first. But you should have your own personal method of making sure you have them all. And you're not accidentally repeating one twice or something like that. All right, anyway, hopefully that allowed you some time to catch up to me. If not, as always, tell me to slow down if necessary. Not M, we take our M column and just flip them over. So we've got false, true, false, true, false, true, false, true. So whatever's in the M column, it just becomes the opposite. For H and R, so we need to use these 2 columns here. Remember, for an and to be true, both of them must be true. It's not just that they agree, it's that they have to both be true. So we have true, true, would give us a true for the and statement. Same thing for the second row. We have true, false for the next 2 rows, which would be false because one of them is false. Next 2 rows are both false, true, which again would be false for the and statement because one of them is false. And then the last 2 rows are false, false, which is still false because, again, for an and statement to be true, the 2 original things must be true. And now we have H and R implies M. So remember, this one gets a bit weird. Remember, with implies, the only thing that's false is a true implies false. Everything else is true. So we have a true implies true is true. Second row, true implies false is a false. Third row is a false implies true is a true. Fourth row, false implies false is true. Next row, false implies true, true. Next, false implies false is true. Next, false implies true is true. And the last one, false implies false is true. Any questions on that truth table creation before I find the conclusion? All right. So again, the point of these is that we have these things that we know are true. So I'm going to go to each one of these columns and mark all of the spaces that are true. So starting with the implication, we have a ton of trues, so we have a true there and then all of these down here. So that one's not helping us out too much, but.
Aaron, someone asked what that last column conclusion is supposed to be again.
Yeah. Oh, this, that's going to be my final answer, which I'll write down in a second. Unless you mean this column that we wrote out here. Are you talking about the empty conclusion one or the filled out one? I want to make sure. The one we just filled out? Yeah. So how do I want to do this? me kind of come off here really quick. So P implies Q if we have P, Q, true, false, true. So we're essentially looking at an implication, and so I've drawn out the basic implication table over here. So remember, the only time an implication is false is when we have a false implies true. And what I was taking here is we had to take this column here and imply it over to the M column. So we kind of had to work backwards. Well, not work backwards, but we had to look at it backwards in a way. So the first one we had a true implies a true, which would give us a true. And then the second one, we ended up with a true implies a false, which is the only case where I had a false. And then everything else started with a false to begin with. Whenever you start with a false in an implication, it doesn't even matter what the other side is, it's true. So that's kind of why the rest of them ended up being true in the first place, is that it started with a false, and a false implies true is true, and a false implies false is true. Did that help? Yeah, I mean, that was weird. So yeah, if you want to think of it as you really only need to be careful if it starts as a true, that's a way to look at it. So yeah, the true, if it ends in a true, it's true, but if it ends in a false, it's false. And then yeah, with the starting with a false, it won't matter. So if you just want to think of it as, oh, it started out false, it's going to imply to a true, that would be fine. I'm a little iffy on saying just do that right ahead, but if it helps you, you can think about it that way. It's just that most mathematicians would get mad at me if I said that that's exactly what's going on. But if that helps you thinking that the only time you really have to pay attention an implication is a true, then I will let you do that. All right. So, any more questions about anything else before I continue to get to the answer? Let me erase this little table over here. And also, thank you for stopping me, person who realized there was a chat. That was very helpful. All right, so we found all the trues in the implied case. Now we're going to look at the not M column, and we're going to find all the trues. True, true, true. And then I'm going to go to the regular R column. Well, there's only one R column, and find all the trues. And then the point is that we want all of these three things to be true. So now we have to look at, row by row. Is there anyone that comes out to all of them being true? So the first row, there's only 2 of them true. The second row, there's only 2. Third, there's only 1. So if we keep going, the only row we have where they're all true is this third one from the bottom. And then for a conclusion, we actually have to remember what we were asked. So if we go back to the original statement of the problem, we are asked, is Andy hungry? So Andy being hungry was our H. So H turned out to be false in this situation. So if Andy is hungry is false, that would mean he's not hungry. So the conclusion we can pull is that Andy is not hungry. Because, let me just put this in parentheses just in case, because the H value was false. So with these, you pull off what you're given in the statement of the problem. You assume that all of those pieces are true once you fill out your really big truth table. You select the row, or remember, I'll scroll back down in a second, but remember, excuse me, from the one before, there was actually 2 rows that satisfied the conditions. So you can have more than one row being an answer. It's just that your conclusion will then be a little bit more wishy-washy. Like in this case, the one we did the other day, we knew for sure that Aaron wasn't late, but we had no idea about Bill because it was true in one row and false in the other. So it's possible to have more than one conclusion. In this case, we kind of have a nice one is just one full conclusion and we just move on with our lives.
Hey, Aaron, quick question.
Mhm.
What was it that determined that we were going to have 8 rows? That kind of just
So it's because of how many variables, if you will, that you have. So here we had an H, an R, and an M. So we had 3. And it's essentially, let me not lie to you. No, that would be the truth. So essentially, if you have n variables, if you will.
double that because it's either on or off. So each one
Yeah.
has a, okay.
So it's essentially going to be 2 to the n rows.
Okay.
So that's why when it's 2 variables, we only needed 4 rows. We will never do anything more than 8 rows, but like if you added on a 4th variable, it would then turn into 16 rows. So they get very large very fast. But that's essentially.
Sorry.
No, so sorry. What you were saying is essentially true. Is essentially because they are both need to be. Sorry, we need to add the true false in each case is why it doubles. But anyway, sorry. Go ahead.
And just to make sure that I've identified those variables correctly, one H, that's one of those statements. Then the other one is R, and then M, and then that 4th one is the combination of H and R implies M. Correct?
So mainly yes. So when I say variables, I mean the ones that,
Just our statements that we're working with. Sorry, variables.
Yeah, so not really the combinations of them. So like the not M, the H and R would not be considered variables. When I say variables, I mean the original ones that we then use to make other things out of. So I'm just talking about the H, R, and the M.
Okay, and then so we have 4 because one of those we're going to say was our not M, and that's why we have the 4 statements that we're working with.
Sorry, we only have 3 statements here, which is why we have 2 to the 3rd would give us 8 columns, 8 rows. So we only have 3 statements here.
Sorry, I'm doing the wrong math. That's why I wasn't getting any. All right, that makes sense. Thank you.
All right. Any more questions about that before we move on to 1.2? So especially if you have a question about a truth table in general. Well, the start of 1.2 has a couple more truth tables.
Can we expect more large truth tables for the next section?
Not large, because essentially what we're going to do next is we're going to develop a way to prove things that doesn't use truth tables. So it's almost like we introduce truth tables and then immediately go on to how can we not use these. But not to say that truth tables aren't helpful and nice in some situations. In terms of some of these proofs, you will probably wish we were still doing truth tables. But there's in the next set of notes there's only 4 row tables, not 8. So
Cool beans, thanks.
And I actually give you the table. Apparently I'm nicer than these ones. All right, 1.2. 1.2. So in the last example from 1.1 that we literally just did, had 3 statements and 8 rows. So kind of what I was just talking about with Vince is for every extra statement, the amount of rows is actually going to double. So if we were to look in something that has more statements, obviously truth tables would get super duper tedious, super duper fast. So like I just said in this section, we're going to look at something to help us manipulate these formulas essentially without truth tables. This is something called propositional calculus. Don't worry, it actually has nothing to do with calculus. It's just called propositional calculus. All right, so definition. A tautology, that's real thick. A tautology, T-A. That is an O. A tautology is a statement that is always true. So say we wanted to look at this truth table that is eventually building up to P and P implies Q implies Q. So let's do this truth table real quick. So we got to start with P implies Q. So of course, remember that the only time that that's false is when we have a true implies false. Everything else is a true. So true implies true is true. False implies anything is true. And then we want to look at P and P implies Q. So we want to look at these two columns, and their and statement will only be true if both of them are true. So we have a true and then a false, false, false. Because in the last 3 rows, there's at least one of them that is false. And then for the last piece, we want to take this essentially and column we just filled out and imply it to the to the Q column back there. So we have a true implies true, gives us a true. A false implies a false is a true. False implies true is true. False implies false is true. So essentially, this above table ends up being completely true in that last column. So we would say that that's tautology because it ended up being true all the time. And actually, this kind of proof table, we can kind of call these truth tables proof tables sometimes. So the above proof table is modeling a rule that we're going to look at in a second called modus ponens. And it's essentially telling us that if we have P and P implies Q, so that's essentially coming from this first bit. If we have P and P implies Q, what we can always imply from that is we can always imply Q. And that's essentially what this is saying, is that if we have those two, we can always imply. And what I mean by imply is if we have that the two of these in the front are true, we can always imply that the Q is true, okay? So if we have both of those, we can imply that Q must be true. So semi-new notation, this kind of double arrow. So if you use double arrows, usually try to avoid it. But a double arrow is going to be used to represent that an implication is a tautology. So if we have an A double arrow kind of implies B, that's going to mean that A regular implies B is always true. Now, to clarify, you might say, okay, well, A implies B wasn't always true. Like if I had a P implies Q, it was sometimes false. It was false in that one case. This is kind of saying this A and this B don't have to be a singular statement. They can be obnoxiously long statements. So this is saying if we have something implies something else and it has that double arrow in the middle, that they're telling us that that implication is always true. So that's what this kind of double arrow notation is going to mean. It's going to mean that it's they're telling us that it's always true. So if they use the kind of double arrow notation for both directions, almost like an if and only if, this would tell us that the regular if and only if is always true. And just to tack it home a bit farther, remember that the if and only if is essentially saying that the implication the one way and the implication the other way. So actually, no, let me, I don't like that. P implies A. You can technically write it with the arrow in the other direction, but usually people will write it so the first thing arrows to the second one. So essentially with this new notation, what's going to happen is we're going to start seeing rules that kind of end up looking like this. So if I wanted to say a statement in the form C and D, I'm going to say always implies instead of like double arrow implies or something like that. I'm going to say always implies. So let me write that down. Always implies is going to be what I mean when I say that. Also, therefore is often used. This one's actually like the legit one. The always implies I literally just made up. So I should probably use therefore, but sometimes I'll probably slip up and say implies. But the therefore is actually legit. People will say therefore when they kind of mean this double implies thing. So if we have a statement where we want to say C and D, therefore E, it could also be written in this kind of format where we have C and then D, and it's telling us that when we combine those together, which is kind of what that little squiggly does, gives us therefore E. So, shifting gears the tiniest bit back to kind of the tautology-ish stuff. A contradiction, on the other hand, is a statement that's always false. That's not how you spell always. And I will slow down a little bit because I feel like I'm going a little too fast. I will take a drink of water. So a contradiction, something that comes out to be always false. So say we want to build up this truth table to end up with Q and not P implies Q. So we would, let's go ahead and do the P implies Q column first. So again, only false when we have a true implies false. If we then want to negate that column, we have false, true, false, false. Just the opposite of what we had in the P implies Q. And then if we want Q and the not column, we would need both of those two things to be true. So we have a false for the first because the second one's false, false for the second row because the first thing's false, false, and false for the last two as well. So this came out to be completely false at the end, so this would be a contradiction. Now with contradictions, there's not really something as nice as, so with the tautologies, it kind of helps us out because then we can say that two things are essentially, it's almost that we can use them to say they're not even, well, I need to be careful with how I say this. Sometimes they can be used to tell us things are equivalent. Sometimes they can be used to tell us that we can just imply one thing from another, which is what we're going to build up to in a second. With contradictions, it doesn't really get us anything nice. It's just like, yay, it's a contradiction. So contradictions exist, but they aren't really used as much as tautologies. Because why would you want to use something that's false? And then a contingency is a statement that is sometimes true and sometimes false. So most things are contingencies. Well, maybe. More things are contingencies than they are contradictions, I believe.
Sounded like an axiom.
Yeah. All right. So we've got tautologies, contradictions, and contingencies. And I'll be honest, I don't think I've ever actually used the word contingency. I'll use tautology and contradiction, but I usually never say the word contingency. So, why do we care? Tautologies are the most important out of the three. So tautologies are important because they essentially allow us to derive new statements. Essentially, we have one thing and we're able to go to a new thing that we also know is true. So two statements, A and B, is going to be said to be equivalent if that kind of double, if and only if, I have no word for that, therefore, essentially that therefore in both directions is true. And so essentially what we can do with these is we're going to have this set of rules of things that are equivalent. So we have these things called equivalence rules, and we're going to have something in a second. Actually, we might not get to it today, who knows. But we'll also have these things called inference rules. Now, in terms of like your assessments, quizzes, and exams, the two tables that we'll be going over, this being one of them, you will have, okay? I'm not expecting you to memorize them. I don't even have all of them memorized. I have some of them committed to memory just because they're used so often, but I don't have all of them memorized, so I don't expect you to have all of them memorized. Anyway, so they have names. So this first one where we essentially have that P is equivalent to not P is going to be called double negation. If we have P implies Q, that is equivalent to not P or Q. This is called implication. And then we have these two that are called the same thing, where essentially we have a not in the front, and we have a statement in the middle that's either an or an and. And essentially what happens, it's almost like we bring that negation inside to both of the terms on the inside, and then the sign flips. It's almost like in math, if you had like 3 minus 5 and a negative out front, you distributed the negative, it'd become negative 3 plus 5. Why did I put a parenthesis back there? It's almost like that. So if you want to think about it like that, that totally works. I will probably be phrasing things in terms of, I'll probably say negation more than I should. So that's the thing. But this is called De Morgan's law. De Morgan's law. So essentially we'll be able to bring that negation inside, make both of the things negated, and then flip the sign in the middle. The next two, essentially notice that the only difference between the two is that the sign stays the same, but the things just flip-flop position. This is called commutativity. So note that that is only happening when it's this, the symbol does not change. Okay, so you can just flip-flop them over. This next one, we have again a set of two, one of them in case of ands and one of them in case of ors. But if all the symbols are the same, should I say both of them? Well, it can be extended to more than two. But anyway, in this case, the rule has two of them. And if one set of them is grouped in parentheses, you can essentially move the parentheses to the other group. So they all have to have the same sign in the middle, but this is called associativity. It kind of works like arithmetic, you know, like 3 plus 5 is the same as 5 plus 3. And if you have 3 plus 5 and then you add 2, it'd be the same as if you did 3 plus 5 plus 2. Same idea. So if it makes sense to you in arithmetic, think about it also in terms of this. It's essentially working the same way. And then this last one we have is a bit trickier to see possibly what's going on. So we have a P on the outside, and then let's just look at this first row. It's attached to an and. And then there's a P or R. So essentially the P and kind of gets distributed to both of them and attached to the Q and the R. And then the or stays in the middle of the two new statements. This is called distribution. That looks gross. I can write that better. And again, it kind of works like arithmetic. If you had a 3 and then a 5 plus 2 and you distributed the 3 in, you'd have a 3 times 5 plus 3 times 2. Obviously, you would multiply them together, but that's technically what's happening is you have the multiplication on the outside now kind of comes to the inside to both terms. All right. So those are our equivalence rules. And essentially what you can do with these is you can replace one side with the other. So I don't know if we'll get to any of the full proofs today, but essentially what we're going to be using for these is, say we're doing a proof and we have a P implies Q. I could then rewrite that as a not P or Q. So essentially these are things that are equal to each other in a way. So you can replace one of them with the other. So I'll hold on like 5 seconds in case people are still writing that down. So say we look at the statement, if you are not shorter than 48 inches and you are not pregnant, then you can ride the roller coaster. If we were to write this in symbols, so let me, I'm going to say shorter than 48 inches is going to be P. I'm going to go with our usual PQR here. You are pregnant is going to be Q, and can ride the roller coaster is going to be R. Notice that I did not bring the knots in at all. I'm going to leave those out as actual knots. So what this would turn into in symbols is if we have not shorter than 48 inches, so not P, and not pregnant, not Q, then gives us our implication, you can ride the roller coaster. So let's look at that first kind of chunk of that. You are not shorter than 48 inches and you are not pregnant. So that was our not P and not Q. Say I want to look at a different statement B, which is it is not the case that you are shorter than 48 inches or pregnant. What that would turn into is it's not the case. Now, the entire case kind of has to go in parentheses because we have multiple things that are considered in this case, quote unquote, shorter than 48 or pregnant. Okay. So it is not the case shorter or pregnant. Give me 1 second. All right, so note that B is actually equivalent to A by De Morgan's. Remember that was the one where we essentially bring the negation inside and flip the sign? Now it's almost like we were using it backwards in a way, but remember they're equivalent, so you can go either direction. So essentially we were kind of taking the original statement A and kind of pulling the negation out of it. That can happen too. But those statements would be equivalent. So I could also, for this entire thing that I was trying to say, I could say it is not the case that you are, if it is not the case that you are shorter than 48 inches or pregnant, then you can ride the roller coaster. So if I were to change it into this, these two things and the English statements that go with them are actually considered to be equivalent. So we have that those two English statements are equivalent. Now, there's a really important note about this type of thing, and it's probably what trips up people the most. When we're going to be using these in proofs, it's not necessarily true that they're going to look exactly like the stated rule. Like if we were looking specifically at De Morgan's, it might not look exactly like not, in parentheses, P or Q, or not P and not Q. Rather, what you really want to focus on is kind of the pattern that happens with these. Because if you had something like not C or R, you can still use De Morgan's on this. This would become not C or not R. Now also, technically, if I'm being super, I should be a bit more stricter than this. What we would actually have to do first is we would need to make a little side step to there, where we would actually need to rewrite the original as not C or not R. And the not R would come from double negation. But technically, that's how it would need to be written in a proof. But essentially that's, so notice what I'm trying to say is that the not C or R doesn't exactly look like De Morgan's because the R doesn't have a not in front of it. But we can still use the rule. It's just that it's going to turn into a not R in the other one. So it's not necessarily going to look exactly like the rule, but you want to kind of look for those patterns. So that's one thing that really trips up a lot of people. So I just wanted to try to clarify that. All right. 225. All right, we should be able to get through. Good. Okay, cool. Questions so far? I haven't really done anything with them, but I don't think we will today, but all right. And then, so we've just looked at equivalence rules.
Back up just like it's one more time. I'm sorry.
No, you're fine.
I just want to get a screenshot of that real fast. Cool sauce. Got it. Thanks.
So we just looked at equivalence rules, and again, we'll be coming back to them in a bit, probably on Thursday. But now we want to talk about a kind of different rule. So an inference rule is oh my gosh, I can't talk. It's going to be used when we know a stronger statement and can conclude a weaker statement. So let's see an option of what I mean by that. So for example, say I have a statement A, Julie pays no sales, Julie pays no sales tax, and if Julie lives in South Carolina, Julie pays sales tax. And then a statement B, Julie does not live in South Carolina. So we want to talk about why is B weaker than A. So notice if A is true, then B actually must be true. Because essentially, well, this is asking us, is that true? And it is the case, yes. If A is true, then B must be true. That's a true statement. So essentially, she pays no sales tax. If we're assuming A is true, we're assuming she pays no sales tax. And if she lived in South Carolina, I'm just going to abbreviate SC, she would pay sales tax. So she must not live. I didn't leave us enough space for this. In South Carolina. So essentially, we're told she pays no sales tax, and we're also told if she lives in South Carolina, she would pay sales tax. So if she doesn't pay sales tax, she must not live in South Carolina. I don't know where she lives, but she doesn't live in South Carolina. So technically, if we know that A is true, we also know that B must be true. But does it follow in the opposite direction? If B is true, does A follow? If we know that Julie does not live in South Carolina, can we also know Julie pays no sales tax? And if Julie lives in South Carolina, Julie pays sales tax? The answer to that case is no. Let me try to make sure I don't run into my own writing here. So no. So essentially, we know she doesn't live in South Carolina, but we know nothing about whether or not she pays sales tax. So we can't assume she pays tax. Or not. We can't assume one way or the other. So, she could live in Georgia and not pay and oh my gosh, not pay sales tax. Or she could live in New Jersey and pay sales tax. So essentially, just because we know she doesn't live in South Carolina doesn't tell us whether or not she pays sales tax. She could not pay sales tax, but live in Georgia. She could live in Jersey and pay sales tax. So we can't imply A if we just know B. Does that make sense? So essentially, in inference rules, what's going to happen, now I say the stronger, which is usually written on the left when the rules are written down, is going to imply the weaker, which is usually written on the right. So the difference between inference rules and equivalence rules is equivalence rules can go in both directions. So with the ones that we were just talking about, I could take something that's P and make it not P. Or I could start with not P and turn it back into P. So I could go both directions. But with the inference rules, I can only go in one direction. So with these inference rules, say I have a P and a Q. Now remember, this notation is essentially telling us that I have P and Q. I can have them separately, I can have them together in an and statement, whatever floats my boat. But if I have both of those, if I have P and I have Q, then I can imply P and Q. This is called conjunction. And remember, that's essentially because the things on the left we're assuming to be true. So if we're assuming P is true and we're assuming Q is true, then P and Q is going to be true because they're both true. Now I erased that little arrow and it hasn't gone yet, so apparently my screen's lagging a lot. Woo! Ooh boy. That's not good. Let me try to reshare my screen. That usually fixes that. Hello! There we go. Our next rule is if we have P and P implies Q. And if we have both of those that we're assuming to be true, we can imply Q. This is called modus ponens. which is the one we looked at the truth table for in the very beginning. Modus ponens. If we instead have not Q and also P implies Q, we can imply not P. So notice that the difference between the two is that we have the implication in both, but then, so we have the implication. Whoop, I was supposed to change to my highlighter. We have the implication in both, but one of them has a P and the other one has not Q. And this is called modus tollens. So very similar, slightly different. Modus ponens, modus tollens. If we have P and Q, so notice that it's no longer this notation, we have to have that actual and statement. We can imply just regular old P or Q. You know, it's essentially just take one of them. Technically, if you were to infer Q, you would have to do commutativity first, put the Q in the front, and then infer. But anyway, so essentially, if you start with an and, you can essentially infer just one of the two things, and that's simplification. I can't spell. Okay, I have it right in front of my face. Here we go. Simplification. There we go. And then our last inference rule is if we're just starting with P or whatever, we can always tack on an or something else because that's not going to change the truth value. Okay, so since an or only needs the one thing to be true, if we already know that P is true, we can tack on whatever the heck we want and it'll still be true. This is called addition. Because we essentially add on that other thing. All right. And just to really clarify, I know I have it written right above it, but I'm just going to clarify over here. Only goes one way. Can only. Oh, how do I want to phrase this? And I see your question, Hunter. I'll answer in just 1 second. Can only replace the left with the right. So essentially we need the thing on the left and we can turn it into the thing on the right, but we can't go the opposite direction. So I'll hold this for a couple seconds because I need to scroll back up real quick. So going back up here really quick, why is B weaker than A? So essentially it's because, so I should maybe write this in here. Since A can give us B, but B cannot give us A, that's technically why B is weaker. And then we go, this is what that's showing, is showing that A gives us B, but B does not give us A. So A gave us B because if we know that she pays no sales tax, and we know that if she lived in South Carolina, she would pay sales tax, then we can imply that she must not live in South Carolina. So essentially, if we know the first statement, we must therefore also know the second one. So A gives us B. A, therefore, B is true. But if we start with B, she does not live in South Carolina, can we assume she pays no sales tax? And we don't even really need to care about the rest of the statement. It's really just that gets us home. If we know that she doesn't live in South Carolina, can we assume she pays sales tax? No, she could live anywhere and pay sales tax or not pay sales tax. We have no idea whether or not she pays sales tax just off of the fact that she doesn't live in South Carolina. So we can't have B therefore A, so B is considered weaker than A. Does that make more sense?
Yes, thank you.
Cool. All right. We got 2 questions left in this section, so let's just finish off this section and then we'll call it a day. So let's write an equivalent statement. Now, I should have probably been careful with the word equivalent because I'm going to be using inference rules as well. But essentially, we're going to write a statement that we can either get from an implication or, sorry, not an implication, an equivalence or inference rule. And in some of these, there's going to be a couple of cases, so I might write down a couple. So in this first one, R and not Q, there's a couple things I could get from this. One of them is if I use an inference rule, if I were to use the simplification here, if I use simplification, I could just get R. So I could get R by simplification. Now I do want to be super clear. Again, technically when doing proofs, we need to do every single little step. So if I wanted to use simplification to get not Q, I would have to use commutativity first to switch them around. So technically I can't get not Q without that extra step, so I'm not going to write it down. The only other one I want to write down is something that I could get by De Morgan's. So by De Morgan's, let me kind of go backwards, if you will, from De Morgan. So I'm starting with the side where the things are technically inside, and I'm going to pull the negation out. If I pull a negation out of this, essentially, since the R started out as a positive, it would essentially end up as a not R. The sign in the middle always flips, and then the not in front of the Q essentially gets pulled out, so it's just I'm going to say negative and positive things a lot because I just think it makes it make a little bit of sense because it works the same way. So, you know, the Q started out negated, so it essentially turns quote unquote positive. The negation gets pulled out. Technically, again, if we were doing this in a full out proof, there would be a tiny little step in intermediate, but I did want to make that that connection between the two. So from that statement, those are kind of the two main ones that we could pull from an inference or an equivalence rule. For the second one, P or R implies not Q. This one we really only have, I believe, one option, and that comes from an equivalence rule. Now there's only one equivalence rule that deals with an implication, which is a thing I'm going to say a lot. So remember, we're looking for patterns. So since we have an implication here, we can use the equivalence rule that deals with the implication. So essentially, if we use implication, which is the rule, so by implication, I'm going to write it this way because I'll run out of space if I try to put it at the end. So by implication, essentially, we take that first thing and negate it. So we have to negate that entire first thing, and it becomes an or the thing in the back. Because let me come over here really quick. The implication rule was if we have P implies Q, we can replace it with a not P or Q. So here, the P is actually P or R. So I have to negate that entire piece. And then the not Q is representing the Q in the actual rule, and that just stays itself. So again, that's what I mean by the not always. Sorry, go ahead.
We know that number 2 is an implication because...
So the main thing is I notice that there's an implication here. And the only rules that I have that have implications in them are the implication equivalence and the modus ponens and modus tollens. But the modus tollens and modus ponens, I said them wrong, both need an extra piece to them that I don't have. So the only thing I have here is the implication. So the only one it can even go to is the implication equivalence. Does that make sense?
Yes, ma'am. Thank you.
So that's the one thing. It's actually super nice when you get an implies in your statement because that really shrinks down the options that you have. When you have an implies, it has to be either implication or one of the moduses. But for the moduses, you need an extra piece, which we'll see how that works next time. But here we don't have that extra piece, so it must have been implication. Any more questions on how that worked? So again, we're kind of looking for patterns here. And again, no, you do not need to memorize these tables. These tables of rules you will have, so you do not need to memorize them. I should say it's good to try to commit them slightly to memory so you don't have to really stare at it forever all the time. Like the ones that are used a lot, implication, De Morgan's are used a ton. So if you can kind of have those in the back of your head where you kind of know those ones pretty well, and can notice those, but you maybe need help by going back to look at modus ponens, modus tollens. I always need to refer back to the moduses because I never remember which one's which and which one needs what and all that jazz. But things like implication and De Morgan's laws, I can usually do by memory. But anyway, so I would try to maybe be familiar with them, but you don't need to memorize them. Yes, both tables that we've looked at, the inference rules and the equivalence rules, neither of them do you have to fully memorize. Again, it's just a suggestion that you get familiar with them. You will have both tables on any quizzes or exams that have those types of things. Okay. So looking at this last one for this one, and then we have one more question and we're done. So here, this actually gives us two pieces. So notice that one's kind of written on top of the other. That's like separating them. So we have one thing that's not R or Q, and then we have a P implies R or Q. Now, since one of the things is an implies, that's again kind of where we narrow down our choices. Now, technically, I could use an implies, an implication on that implies at the bottom. But since it has this other piece attached to it, it's probably going to be a modus. So let's figure out which modus it is. So notice we have a not on the thing that's by itself, and that's not in the implication. Unfortunate use of the word not. So essentially the thing that's by itself should be negated. So it's looking like it's probably gonna, well, I should also say it's the thing in the back that we have separate. So that's the other thing. But it's looking like it's modus tollens because we have essentially the setup for a P implies Q. The Q is a bit more complicated, but we have the setup, and then we have the negation of that quote unquote Q. So with the both of these, we can imply not P, which is actually what we're going to fully imply here, but that's because this was also a P. We can essentially imply the negation of the first thing in the implication, which in this case is just P. And this would be my modus tollens. So since we had an implication and we had more information about the back piece, it looks like modus tollens and it did follow the right pattern, so we're good to go. If we had more information about that first piece, if we were told just regular old P, then it would have been opponents. So that's the other thing to look for is what does your other piece deal with? Does it deal with the hypothesis or the conclusion of the implication? Does that make sense why that's modus tollens? Okay.
Sort of.
It takes practice. That's the other thing. This does take lots of practice to be able to figure out how they go. Again, the main tip I can give you is look for patterns. Don't get bogged down in specifically P implies Q. Think of something implies something else, and those two things can be whatever the heck they need to be. So one last thing in the last few minutes, another type of question that I can ask with these types of things is something where we justify each conclusion with either an equivalence or an inference rule. And so the first thing we kind of need to do with these is the best thing we can do is to write them in symbols. Yeah. So let's go ahead and write this in symbols. So if Mandy is a graduate student, so let me let the is a graduate student just be P. You can use whatever letters you want, but I'm going to use P, Q, and R here. So if Mandy is a graduate student, then she is tired. Oh, I feel that from when I was a grad student. That is true words. In other words, so this kind of like cuts us off to a completely new thing. That's supposed to say Mandy. Many. Mandy is not a graduate student. Or she is tired. So I kind of went a little farther to get the or she is tired in there. So we have P implies Q. If Mandy is a graduate student, then she is tired. And then we also have not P or Q. So essentially what I need to do is I need to figure out what rule connects these two. I should be careful with using a double arrow. I want to know how to get from one to the other. Which rule deals with it. So again, since one of the things is an implies, we narrowed down our rules a lot. 3 rules that deal with implications, implication, and our modices. Modus needs 2 things to be able to imply something else. We only have one thing heading to one thing. And if we look at our implication rule, it's a P implies Q that goes to not P or Q. So this would be by implication. So the implication rule is what can get me from a P implies Q, the if Mandy is a graduate student, then she is tired, to the equivalent statement of Mandy is not a graduate student or she is tired. And this final one, where I didn't capitalize the second muffins, Muffins is not a cat. If Muffins is fluffy, then she is a cat, therefore Muffins is not fluffy. So let's say Muffins is a cat. Let's go ahead and use some different letters here. Let's just use C there. So we would have a not C. If Muffins is fluffy, so let's use an F, then she is a cat. So we have an F implies C, and these are kind of separate statements. Therefore, Muffins is not fluffy, so not F. So essentially, the thing we're looking for here is kind of also the place where you kind of stop knowing what you have versus what you want. In the first one, we had this phrase in other words, and then here we have therefore. If you have something like that, therefore, in other words, those are the 2 main ones I can think of. I really can't think of anything else I would use there. That kind of tells you where you stop having what you are given and you switch to what the result is. So essentially what I'm saying is we start with not C and F implies C, and we want to know what can get us not F from those 2 things. Nope. So if we go back to our rules, again, we have one that has an implies, so we're again shrunk down a ton between our implication or our modices. But here we have 2 pieces instead of just one, so it looks like it's going to be a modus. So now which modus is it? So notice that the extra piece of information we have is kind of attached to the conclusion of the implication instead of the hypothesis. So the only one that deals with giving us extra information on the conclusion is modus tollens. Now let's triple check that modus tollens fits here. We would need a P implies Q. Okay, we have F implies C. And we would need a not Q, so we would need not C, which we have. And what does that get us by modus tollens? It gets us the negation of the hypothesis, which would be not F, which is exactly what we want, so this would be my modus tollens. I may have talked through that way too fast. Essentially, all that I just babbled about was essentially if we look at the actual rule of modus tollens, it follows the correct pattern, just with different letters. So that's another type of question that I can ask with these types of things is I can give you actual statements and then ask you what rule is used to get that. Or I can also ask you something where I give you something and then I ask for a statement that you can get from that original thing. You'll see more of those later on, but that's kind of the other type of question that I can ask, not just necessarily in symbols, but with words. Let me erase the statement of the rule just in case that is confusing when people look at it later. All right, questions, concerns on either of those 2?
It's a whole lot of implications.
Yeah. So, okay, so let me just babble real quick. We've got technically 5 minutes of official class. I'm probably not going to take 5 minutes. And my voice is dying. So on Thursday, what we'll look at is we'll actually look at essentially using these. We haven't really used these yet in their full capacity. So what we're going to do on Thursday is we're going to look at proofs and how to actually use these to prove things. So that'll look like this kind of thing right here. And so we'll talk about that on Thursday. you also have a quiz on Thursday, your first kind of official one. Now, since we didn't get to proofs today, that means that I can't put proofs, or I usually don't. I usually don't put anything that you would be learning that day on the quiz, because that's just mean. So that means that your quiz on Thursday, and I'm typing this out in chat. Actually, well, I could ask you some questions like the ones we just did right here. So you'll definitely have a truth table on there. Or two. I will probably not go for an 8 row. It'll probably be a 4 row. It could be, you know, a 5 or 6, 7 column thing, but it'll only be 4 rows. So you'll have truth tables on there. And then I think what I do want to do is some equivalence, and inference rules in terms of statements. And I'll say like problem 5. So that's, I spelled inference wrong, but that's in chat right now. So essentially what I mean by that is this problem 5 that we just did, there would be a question, maybe 2 like that on the quiz as well. So definitely a truth table or 2, and then equivalence and inference rules in terms of statements. Again, you will have the equivalence and inference rule tables available to you. And so this is kind of what I try to do on Tuesdays. I try to give you an idea of what's coming up on the quiz on Thursday. And we'll do a warm up on Thursday dealing with those 2 things as well, because my quizzes are not supposed to be something terrifying. They're just supposed to help you figure out if you know it well enough to take a test on it later. Anyway, my voice is leaving me. I'm going to stop talking now. If you have any questions, feel free to stick around for a little bit. Otherwise, I will see you on Thursday. Have a great day. Yeah.
Thank you.
Thank you.
Thank you. See you Thursday.
Jessica. I am gonna go with no. I've been battling that back and forth in my head. She asked, are we allowed to use the notes on the quiz? Because I know with it be fulling online.
Yeah, how are you going to stop us?
Try to be sneaky anyway. I would suggest trying to do the quizzes without your notes. I will be allowing the exams to be open notes, but the more you know in your head, the easier it's going to be. Because don't think open note exams are going to be super nice and easy and a breeze. Because if you don't know where to look in your notes and you have to look in your notes for every single question, then you're going to feel sad. So I would suggest trying to do it without your notes. My quizzes are not supposed to be terrifying things. Best way to prepare for the quiz, I would say look over your notes in terms of the things that I just told you, truth tables and equivalents, and the things we just said. You can easily Google truth table questions. This problem 5 one would probably be a bit harder to find, especially on our level, because there are a lot of rules that we don't cover. But you can probably, especially with truth tables, Google pretty easily. I do agree. Sometimes notes don't help in assessments. But anyway, I would look over your notes, look over the problems that I mentioned, truth tables, and this problem 5. Again, we will be doing a warm-up on Thursday. So when you come on Thursday, if you can't do the warm-up, ask me questions to make sure you understand it before we stop. Because the warm-up is very similar to the quiz. Nudge, nudge, wink, wink. So yeah, the homework, so it has inference rules in general. Let me triple check if it has inference rules in this fashion. I want to say yes, but give me 2 seconds and I'll look it up real quick. Oh, it's mad at me. Come on, be fast, computer. There we go. Good job. Oh, I should have put those on the quiz instead. Oh well. Oh, yeah, there are some like this on your homework. There's a justify each conclusion with the derivation rule question. Another one. So there's a couple questions like this problem 5 on your homework. So you could also look over those before Thursday if you wanted to try to get some extra practice.